Okay, bye.
I wonder why he's called us here today.
I'm not sure. Alright, I've called you guys here to discuss your work ethic and performance this past month. James, I've been really impressed with you. I'm gonna up your salary to 50 grand.
What? That's so unfair. I work so much harder than him. This is sexism.
I'm gonna need to see some more effort from you. Look to James as a role model.
What? This is ridiculous.
Thanks for coming in.
This for the hood! This for the ghetto!
I wanted to come talk to you today about a problem I'm having.
What can I help you with today, Danielle?
Well, I've been working my ass off for this company for the past year, and all my hard work goes unnoticed. Meanwhile, this scumbag over here, James, gets a raise for slacking off. What's the meaning of this?
I think this reflects the differences in salaries between men and women in Canada. Give me a minute to analyze and investigate this issue using two sample case hypothesis testing.
So far, we have learned the one sample case, which is concerned with the difference between a sample value and a population value. We will now speak about the two sample case, which is concerned with the significance of the difference between two separate populations. The question we are asking when using a two sample case is the difference between the samples large enough to allow us to conclude with a known probability of error that the population represented by the samples are different? There are 5 steps to this process. Step 1. Making assumptions and meeting test requirements. We must assume 3 things. First, independent random samples. Second, level of measurement is interval ratio. And third, sampling distribution is normal.
In independent random sampling, the two-sample situation requires that the sample be selected independently as well as randomly. This requirement has been met when the selection of a case for one sample has no effect on the probability that any particular case will be included in the other sample. This can be satisfied by drawing EPSEM samples from separate lists. It is usually more convenient to draw a single EPSEM sample from a single of the population. Each case in the population must have an equal chance for being selected for the sample, and then subdivide the cases into separate groups. For example, in our case, we will be comparing males and females.
Step 2. Stating the null hypothesis. The null hypothesis states that the population represented by the samples are not different on this variable. A researcher must also decide between a one-tailed and a two-tailed test. If the researcher is concerned only with the differences in a specific direction, a one-tailed test can be used. On the other hand, if a researcher is unsure about the direction, the research hypothesis states only that the population mean is not equal to the value stated in the null hypothesis. This format is called a two-tailed test. In our case, as we are comparing male and female wages, we are predicting that females earn less than males, therefore a one-tailed test can be used. The equation used for step 2 is hypothesis 0 is mu1 equals mu2, or hypothesis 1 is mu1 does not equal mu2. In our case, mu1 is wage of females and mu2 is wage of males. Hypothesis 1 is our research hypothesis, whereas hypothesis 2 is our null hypothesis.
Step 3. Selecting the sampling distribution and establishing the critical region. For large samples, we will be using the standardized normal distribution to find areas under the sampling distribution. If alpha is set at 0.05, the critical region will begin at the z-score negative 1.65. With small sample sizes, the t-distribution is used to establish the critical region. To utilize the t-distribution for testing two sample means, we need to perform one additional calculation and make one additional assumption. The calculation is for degrees of freedom, a quantity required for proper use of the t-table. Degrees of freedom are equal to n1 plus n2 minus 2. Moreover, when samples are small, we must assume that the variances of the populations of interest are equal in order to justify the assumption of the normal sampling distribution. Simply, assume equal population variances. Since our sample size is over 100, we will be using a z distribution with an alpha of 0.05.
Step 4. Computing the test statistic. To evaluate the probability of any given sample outcome, the sample value must be converted into a z-score. Solving the equation for a z-score equivalent is called computing the test statistic, and the resultant value will be referred to as z obtained. If the population standard deviations are unknown, we must use a formula to estimate the standard deviation of the sampling distribution. This value will then be substituted into the first formula, and z obtained will be computed. With small samples, a different formula is used for the pooled estimate of the standard deviation of the sampling distribution. This value is then substituted directly into the denominator of the formula for t obtained. The equation for z obtained is x bar 1 minus x bar 2 all over population of standard deviation x bar minus x bar. Sample 1, women. The mean is 30,850. Standard deviation, 1,389.84. Total number of cases, 10. Population of standard deviation, 1,318.52. Sample 2, men. The mean is 47,330. Standard deviation, 977.58. Total number of cases, 10. Population of standard deviation, 92.42. Population standard deviation x bar minus x bar equals the square root of standard deviation 2 squared all over n minus 1 plus standard deviation 2 squared all over n minus 1 equals the square root of 1,389.84 squared over 9 plus 977.58 squared over 9. This equals the square root of 214,628.36 plus 106,184.74, which equals the square root of 320,813.1, which brings us to 566.4.
Z obtained equals x bar 1 minus x bar 2 all over population standard deviation x bar minus x bar, which equals to 30,850 minus 47,330 all over 566.4, which equals negative 29.1. Step 5. Making a decision and interpreting the results of the test. If the test statistic falls into the critical region, we reject the null hypothesis. If the test statistic does not fall in the critical region, we fail to reject the null hypothesis.
Our z obtained is negative 29.1. Our z critical, negative 1.65. Negative 29.1 is more extreme than z critical, therefore we reject the null hypothesis.
In this demonstration, we'll use the independent sample t-test to test for the significance of the difference between men and women and how often they go out in the evening to engage in leisure activities. If there is a statistically significant difference between the sample means for men and women, we can conclude the population. All Canadian adult men and women are different on this variable. In the first block of output, group statistics, there are some descriptive statistics. There were 747 males in the sample, and they participated in 28.64 activities during the evening in an average month, with a standard deviation of 17.233. The 765 females went out an average of 23.68 times per month, with a standard deviation of 16.938. We can see from this output that the sample means are different and that, on the average, males go out in the evening more often. Is the difference in sample mean significant? The results of the test for significance are reported in the next block, independent samples test of output.
We produced an error bar graph for the confidence interval for the mean. The error bar graph is especially useful when comparing two groups because we can quickly assess if there is a statistically significant difference between the two means. To produce an error bar graph of the 95% confidence interval, first click Graphs, Legacy Dialogs, and then Error Bar. Next, click Define. Transfer the dependent variable NumiVact to the variable box and the independent variable sex to the category axis box, and then click OK. Following the error bar graphs will be produced. The error bar graph shows that the sample means are different and that on the average, males go out more in the evening than females. Further, the confidence intervals do not overlap, so the two means are significantly different from one another.